Here we go into the last kind of geometric series problems for this lesson before we get into the exercises, but they're goodies. So in this one, you're given basically an expanded form of a series and you're told, find the sum of the series. I've seen this a lot on BC exams as well as in many college Calc 2 courses. So what do? Well, there's two ways of approaching this. First thing is, if you're asked to find the infinite sum of something, there's a chance, pretty strong one, that it's geometric. So how do we tell if that's the case? Well, you look at it, and if you can right away tell that it's a geometric series by seeing what you're multiplying by to get from this term to that one, then you know it's geometric if it's that same common ratio. If you don't know, then look at the terms and divide this term by that one to get a common ratio. So 12 divided by 16 ends up being 3/4. 9 divided by 12 also ends up being 3/4. And then 9, well, times 3/4 is going to be 27/4. So we kind of sniff that out. And sure as there is sunlight on many days, we've got 3/4 times each term gets us to the next one. So find that common ratio. If you're not sure of it, divide the next term by the previous one to get the common ratio. That's what the common ratio is. In general, actually, it's always going to be the next term divided by the previous one, right? Or a sub n plus 1 divided by a sub n, if you will. So you could look at r as a sub n plus 1 divided by a sub n if you really want to be fancy. Okay, anyway, looking at this right here, we now have our first term, right? Call that a sub 1. And then we have r. So I've got a sub 1 equals 16. I've got r is equal to 3/4. We know that the sum of this thing is going to be equal to the first term over 1 minus r, which in this case is equal to the first term, 16, over 1 minus 3/4. There you have it. So just be careful simplifying that out. That 16 divided by 1 minus 3/4 is 1/4. And that will simplify down to 64, 16 times 4. That's the sum of that series. Some other people would prefer doing it this way, rewriting it as like n equals, let's say 1 to infinity, the first term times, and then they write it out as 3/4 to the n minus 1. That would give that first term, and then they see that r is 3/4. A sub 1 is 16, and they go to town from there. I don't do this unless I'm asked to. So unless you're asked to put in sigma notation, no reason to. All right, but they're one and the same. They're equivalent. This is just the shorthand of that expanded form of the sigma notation. All right, let's do one more. There can be x's? What? So I keep feeding you these ideas of having variables here and there. You might have noticed that a little bit in, I guess it would have been lesson 1 of this chapter. And I'll keep doing that to you because eventually we're going to be seeing these things called power series coming into play. Those are just infinitely long polynomials, which actually do the world a lot of good. We'll see that down the road. Not much in this chapter, but in the next one. I'll keep preparing you for it though. So what's the sum of this series? It's going to be in terms of x. Well, what we have here is we've got x plus x squared plus x cubed plus x to the 4th. To get every preceding term to the next term, we're multiplying by x every time, and so on and so forth. So what that means is our common ratio is r, which is x. And the first term, if you want to call it a sub 1, is equal to x as well. So overall, we know that the sum of this series, again, is going to be a sub 1 over 1 minus r, which is equal to a sub 1, which is x, over 1 minus r. Oh, so the infinite sum of that series is this, but I'm going to say provided that, and that's where this question goes, we need the absolute value of r to be less than 1. So it says, for what values of x will that series converge? Well, it's only going to converge to this if the absolute value of r is less than 1. And r is the absolute value of x, which needs to be less than 1. Well, if we've got the absolute value of something less than 1, that means that we're between 1 and -1. And we're not going to include -1 because if we did, we would have x equal to 1, and that would be a diverging geometric series. This is actually known, believe it or not, we'll go over this far down the road in the next chapter, as the interval of convergence. It's the interval over which all x values we plug in here will converge. So if I use like 1/4 in here, we'd converge. But if I used 5 for x, we would diverge. We can see this a different way. We can write this as sigma from n equals, let's do it from n equals 0 to infinity, where the first, actually, you know what? Might be better if I do it n equals 1. And that'll make a lot of sense. what we're doing here then is we've got x to the n. Your first term was x, then x squared, then x cubed. And again, it will converge on this interval. And just to see that, let's say we were to pick a number from outside that interval, like 2. We right away see that this would be a diverging geometric series with r being greater than 1, the absolute value of that. But if I picked something like 1/4, which is well within that interval, even if it was negative 1/4, to the n, now all of a sudden that thing's going to converge by the geometric series test. So what does it converge to? A over 1 minus r, which means this infinitely long polynomial is equal to this very short rational function, interesting, as long as x is in this window. Oh, it's beautiful. I'll see you in the exercises. Until then, peace.